So welcome to rhythm class. So today we're going to have a verbatim lecture. That is a random. This lecture is only for the entertainment purpose. Actually, this is not in any curriculum. You will get this chapter, and this is only for educational purpose. When I was in high school, my physics teacher, whose name was Mr. Bader, called me down one day after physics class and said, "Look, Bert, I want to tell you something interesting." Then he told me something which I found absolutely fascinating, and I have since then always found fascinating. Every time the subject comes up, I work on it. In fact, when I began to prepare this lecture, I found myself making more analysis on the thing instead of worrying about the lecture. I got involved in a new problem. The subject is the principle of least action. This is the topic we're going to study in moments later. So what was the chapter? It is here. Mr. Bader told me the following. Suppose you have a particle here, a time tune, and a gravitational field, for instance, which starts somewhere and moves to some other point by free motion, like this. When you throw a particle like this in the gravitational field, it goes like this. Yeah, it goes like this. It's a projectile motion. And this is the T2. This is here particle. This is there particle. Motion is this, and this what we call actual motion. Yeah. Now, it goes from original place to the final place in a certain amount of time. Okay, it goes from the original place to final place in a certain amount of time. Now try a different motion. So suppose it get from here and follow this trajectory. This is the same. Okay. Time t2 it is there. This is what we call imagined motion. So let's repeat what I've said, that the particle which is in the gravitational field, suppose it for instance, and then it goes at instant at time t1 it was here, and then by following the trajectory which is under the gravitational field, then it comes here there. Okay, now suppose another particle which follow different trajectory. This is known as actual motion, which happened actually, and this is what we call, which is called imagination. Let's suppose a particle travel this motion. Okay, so if you calculate the kinetic energy, it's every movement on the path. Take away the potential energy and integrate it over the time during the whole path. You'll find that the number you'll get bigger than that of the actual motion. So this is bigger for what? This is bigger for this. Just I have what I have written. Let me illustrate a little bit better what I mean. if you take the case of the gravitational field, then if the particle has the path xt, let's just take one dimension for a moment. We take a trajectory that goes up and down, not sideways, where x is the height above the ground, and kinetic energy of half mdx by dt square. What I've said is this, that suppose this, we take the particle like this, graph. Let's make the graph for that. This is only the height, x is only the height, okay? It means what I said, that it will move up and down, not sideways. Is restricted here, suppose one dimension, okay? What I said is 1D, and here you'll get the time. Now what will be the path? Like this, in the gravitational field. Okay, this is his. Here. Okay, this is at T1 and this is at T2. Okay. Now this is for the actual motion. Now what for the imagined motion? This will like this. Okay, so this is the actual motion, this is the imagined motion. Okay, so what I wanted to say, that we just calculate the kinetic energy. We just calculate the kinetic energy for this and subtract or minus the potential energy of that particle at that moment, and when that kinetic energy and minus potential we got, we just subtract, we just integrate over T1 to T2. Let me explain you, not verbally, mathematically or written. Kinetic energy minus potential energy for a small period of time, and then it is over time T2. What suppose the mass m is the mass of the particle. So what will be the kinetic energy? Half of into m. Velocity will be change in the displacement. V square minus, what will this, mgx, this over dt, integrate T1 to T2. So he said that this will be greater for this and lower for this. This was the principle for least action. So this is what we call action. Let's try with a different example. Okay, first suppose, let's keep this blank, let's now listen me. First suppose we take the case of free particle for which there is no potential energy at all. Now check this, if there will be no potential energy, then the rule says that in going from one point to another in a given amount of time, the kinetic energy integral is least. So it must go at a uniform speed. We know that's the right answer to get a uniform speed. Why is that? Because if any particle were to go any another way, the velocity would be sometimes higher and sometimes lower. The average velocity is the same for every case because it has to get from here to there in a given amount of time. As an example, say your job is to start from their home and to go to school in a given length of time with the car. You can do it several ways. You can accelerate like mad at the beginning, slow down with the brakes near the end, or you forward can go at a uniform speed, or you can go backwards for a while, then go forward and so on. The thing is that every speed has got to be, of course, the total distance that you have gone over the time, but you do something, anything, but you're going too slow. Now the mean square of something that deviates around an average, as you know, is always greater than the square of the mean. So the kinetic energy integral would always be higher if you wobbled your velocity than if you went at a uniform velocity. So read that the integral is minimum if the velocity is constant. What I said, I just write on the paper right now. What I said was that kinetic energy when go uniform, okay, is less than the kinetic energy with variable one. Case when the average is constant. So let's try this. Just make the graph for this. When there is no force, this is 3. Okay, this is here from there. Okay, no forces. Just t here time t1 and time t2. Now another graph. From here, there. More kinetic energy, more potential energy. So at last there is something which I can't tell you, is then I'm going to have a new complexity, to introduce a new complexities in your life. The kind of mathematical problem will have is very difficult in the new kind. We have a certain quantity which is called action, So action is defined, is written as S is equal to the time integral kinetic energy minus potential energy. That was just saying that we calculated in this. So this was that. Remember that the potential energy and kinetic energy are both functions of time. For each different possible path you get a different number for this action. Our mathematical problem is to find out of what curve that number is the least. So this action was least for this, as for this, which was the actual action, and greater for this, which was the imagined path that we supposed. But watch out, ordinarily we just have function of some variables and we have to find out the value of what variable with the functions is least or most. For instance, we have a rod which has been heated in the middle and heat is spread around. For each point on the rod we have temperature, and we must find the point at which their temperature is largest. But now for each path in a space, we have a number, quite a different thing, and we have to find out the path in space for the number is the minimum. This is a completely different branch of mathematics. It is the ordinary calculus. It is not the ordinary calculus. In fact, it is called the calculus of variation. we call it the calculus of variation. We'll continue this in next video. Let's write beautifully. Thank you.